Sagar, should I admit all now then?
Yes, sir. Already admitted.
Okay. But people can have their videos on, some people. Can you check the settings if so that they cannot turn on their videos unless requested?
Okay, okay.
The start video was on, Sagar, okay? So this has to be changed. People should not start their videos. So welcome everyone for this first lecture and the beginning of the introductory summer school in astronomy and astrophysics, as well as the RCAA, the refresher course in astronomy and astrophysics targeted towards the teachers and associates in the universities. So we'll have a joint session here comprising of participants both from the summer school, who are usually bachelor's and master's students, as well as more experienced teachers attending the refresher course. So for the refresher course participants, a grand welcome again. And any specific messages for that is targeted towards the refresher course would be communicated to you by the team members organizing the course, led by Professor Saikia. And for the rest of the participants, a very warm welcome to the summer school. So we have a pretty interesting lineup of lectures, both basic as well as pedagogical, and more advanced as the summer school progresses later on. And we also have lined up very interesting demos and experiments. All of these would be demonstrated to you online in some of the afternoons. So I'm just waiting for a few more people to join, which I can see they are waiting in the waiting room. And after they have joined, so we will start the lecture, and I'll just give you a brief demo of where you can find the different resources meant for the summer school. So there are 5 more people to come. Okay, I think we can start now. So once again, welcome to you all. And just for introduction, I am Dipanjan Mukherjee, a faculty in IUCAA, and I am one of the faculty coordinators trying to organize various aspects of the summer school in collaboration with the members of the Teaching and Learning Center in IUCAA, led by Professor Saikia. And before I go to so the first lecture today is on radiative processes. But before I go to the lectures, I felt that I should give you a brief introduction of what you will be expected to do in the course of this lecture series, and to make you more acquainted with where the informations will be said. So firstly, these lectures will be live streamed on YouTube. You can, the live stream link has been shared with you, as well as it's available on the IUCAA website for the summer school. And after each of these lectures, the recording of the lectures will be available for you again. So in case some of you have any issues with your internet speed or the connectivity, you can always go back to the recorded lecture and continue and join there. So this year we have a substantially large number of participants compared to what we usually have. And it's a very great thing to have so much of interest, but we will be slightly constrained in terms of the interactive sessions and question answers from you. So we are still thinking of various ways of how to get your inputs in. Maybe we'll send out in between the lectures series, we'll send out some forms to you where you can add any questions that you have. But the way it will usually go is for each lecture, we will have a 1 hour lecture. 5 or 10 minutes before the end of the lecture, the instructor would end the session and not end the session, end the lecture, and ask you for your questions. Now, we can only handle a few of these questions during the live session. So the way you will have to do it is in your Zoom platform, if you have the new version of Zoom, you'd find that there is a reaction button at the bottom right. Once you press the reaction button, you'll find there is an option to raise hand. And if you press the raise hand, then your name with a hand raised like this will appear in the box of participants. Okay, yeah, I'm seeing a few of you are testing it. Good. So this is how you actually raise hands. So at the end of the sessions, when I or the other instructors ask you to raise hands, you can raise your hands. We will try to accommodate as many of the questions as possible. But of course, I'm sure you'll all have interesting questions to ask, which we may not be able to address live because we almost have, as you can see, 700 participants, which is a great number. I'm very happy to see the enthusiasm of all the members. But then we will try to circulate some Google Forms to you where you can write down your questions and get back to the instructors. One thing is, if you have any questions, do keep a pen and paper with you and write it down so that you can remember the question, and so that when we do try to get some feedback from you, you can ask, you can send those to us again. Now, this is how the Zoom works. So I'm sure now that we have almost 700 plus participants, you all have received the Zoom invite. So you can all lower your hands, please. So if you go to the reactions tab again, please lower your hands. You can have raise hand and lower hand. So lower your hands, please. Thank you. So you must have all received the Zoom info as you have joined here. In case you have not, then please check your emails. Please do not pass on this Zoom link to your friends because we are limited to 1,000 participants, and we do not want to have in a situation where more than one person who are not selected for the summer school joins and genuine candidates are left out. Although that is not supposed to happen because we have placed security measures, but I just wanted to let you know. Now, regarding the more further material for the summer school, all of you would also have been sent an invitation to join the PB Works website. So I'll share my screen and show you what it is. So I'm sure all of you can see this screen now. So this is the website of the PB Works. Okay, and here is an introductory message. So what we will do on this website is we'll have a more detailed breakup of the lectures for each day. And if there are any relevant information that needs to be communicated to the participants, we will present it in this column of the miscellaneous info. For these 3 lectures today, you do not have any extra information that you need to access. However, for certain lectures, especially for the demonstrations, you might need further information which the instructors are already preparing, and some of it has also been supplied. Although we will try to put in the links here, but just to let you know, there is a pages and files here. And from there, you can access or you can view some of the pages. For example, under the pages and files, there will be something called the Stellarium worksheet. So this is relevant for the demo session on the Stellarium software that will be demonstrated to you on the 12th. Okay, so in the front page, you will have the some basic reminder about how you can join these sessions. And if you already, I'm sure you all have access to the lecture schedule. So you can, but the schedule is also given here. If there are any changes to the lecture schedule, it will be updated on this website. So we will also try to communicate by email, but keep an eye on this website every day before the start of the lectures for any additional information. The other thing is you have all received a link on to join these lectures using Zoom. the same link will be valid for all the lectures of the day and throughout the summer school. So you don't have to hunt for links besides what has been already sent to you. It's the same unique link. If we do find the need to change the link, we will again communicate it to you separately. But for now, use the same link to join all the lectures. Okay, so before I proceed to my lectures, I will first like to see if there are any questions. Audio is not audible. Prakash, if you can unmute yourself and say whether you can hear my audio.
Yeah, I do hear you loud and clear.
Okay, thank you, Prakash.
I think it must be a problem with the participant.
Yeah. So if you have not received any link, then please write to the ISSAA the email. Okay, so if you have any questions other than that you have not received that link, then raise your hand. I can see Saicom, I'm asking you to unmute yourself. So Saicom, can you ask your question? You have a raised hand.
Hello, sir. Good morning.
Are you unmuting or should I unmute them?
Yes, Saicom.
Will we get certificate after the end of this summer school?
Saicom, a certificate.
Sir, will we get certificate?
Yeah, a certificate certifying your acceptance to the summer school will be provided. So thank you for this question. I should clarify that a certificate will be provided to all the summer school participants. This is only for the summer school participants, not the refresher course, who will have the certificates given to them separately in a different way by the refresher course coordinators. But for the summer school participants, a certificate certifying your acceptance to the summer school will be provided to you. The method to download that will be informed to you by this week. No other certificate of participation or completion will be provided after this, because this is a learning experience and we really cannot really judge online presentations like this. So a certificate of your acceptance will be provided to you. Yes, Saiko, I'm unmuting you, and please lower your hand.
Thank you, sir.
Okay. Yuvraj, you have a question? I'm unmuting you. Yuvraj, do you have a question?
Am I audible?
Yes, Yuvraj, you're audible.
Yeah, good morning, sir. So I could see certain worksheets are being available in the PBS work website.
Yes.
And if you could finish those off, what is the way that we could submit it to you?
The worksheets and all these things will be communicated to you by the instructor when they actually work on it, okay? So you don't need to worry about it now. So when a particular course or a particular lecture comes where the worksheet is relevant, the instructor will inform you regarding that.
Fine, thank you, sir.
Thank you. So I will just take two more questions, and if you have anything else, you can write on the chat. So the next is Priya.
Greetings, sir. I have a little question regarding the PB Works website.
Yes.
It's pretty lagging in nature, and it's difficult to log into it or even access pages. From clicking anything on the website, it takes too long, and there are several crashes because of which worksheet links and
I think I have also noted your email query that you had sent. Maybe you were the person. Unfortunately, this is what we have right now. We will try to investigate the reason of the lags. I had talked to my system administrator in the morning regarding this. We are not really aware of why this is happening. And today in the morning, PB Works was working fine. I also had noticed the slow response of PB Works yesterday, but maybe it could be an issue on their part. Since we have a lot of participants for the summer school, more than 900, if a lot of people access the PB Works at the same time, it can cause lag, but I'm not really certain that that is the cause. It maybe the server on PB Works was not working. So we will see how it works. If there are persistent issues, since this is a 1 month summer school, we will try to think of some alternative methods. Thank you, Priya. Okay, last question, Spurti.
Good morning, sir.
Good morning.
Sir, can you guide us on research projects or review papers?
That is not really relevant for this discussion, Spurti. Hope you learn more about that while attending the lectures in the summer school and get some ideas of your own. And I hope that for all the participants, or the young, especially the young participants who are completing their bachelor's and masters, you get more motivation to learn more about astronomy and astrophysics, and this experience spurs you to take up a career in astronomy, and that is what we will always want. So I hope this summer school is exactly meant for that, and at the end of it you get some more insight into it. Thank you, Spurti.
Thank you, sir.
So the rest of the people, please lower your hands and you can write the questions in the chat box. I will try to address them later on. So now I will start my lecture. Let me share my screen. Okay. Okay, so the first lecture would be by me, and we'll continue that for 2 or 3 more lectures after this. It will be on radiative processes. And this lecture, for references, I can say that one of the most widely used reference for this, especially for people working on astronomy and astrophysics, is this book by Ripicki and Lightman. It's called Radiative Processes in Astrophysics. It's quite expensive. You may find a copy online somewhere, but I'm not sure. But this is the best reference that we have from where we actually have learned when we were students. Another very important and interesting book is called The Foundations of Radiation Hydrodynamics by Dimitri Mihalis and Barbara Mihalis. Now, this is about radiation hydrodynamics, but the main body of the book really talks about radiative processes, how you can model radiative transfer. That is how radiation is modeled and progresses in time and space. And this is also a very insightful book, a bit advanced. So if you are interested in this, please go ahead and learn. But this is not something that we really refer to often, but only for specialized circumstances. And then there is, of course, the Classical Electrodynamics by Jackson. Now, I'm sure all of you would be familiar with this book, especially those in your masters and maybe late bachelors. This book is elementary in that sense because it's often referred to in bachelors and masters, but it is widely used even now at advanced levels. And in astronomy and astrophysics, several of the radiative processes would require you to have a fundamental understanding of electromagnetism itself, especially electromagnetism in moving medium. For example, radiation from charges, moving charges, what is the light cone, etc. And all of these are extremely well demonstrated in Jackson. And I can tell you that if you do want to develop a career in astronomy, understanding the basics of electromagnetism is a fundamental and important criteria. And because in astronomy, what we really gain information about everything outside our terrestrial region is through the electromagnetic radiation that is coming towards us from those objects. Of course, nowadays we also have another window, which is the gravitational wave radiation, that gives us a different opportunity to understand large-scale systems elsewhere. But astronomy is based on electromagnetic radiation, and so understanding the radiative processes, charges, radiation from moving charges, etc., is extremely crucial and fundamental. So these are the references, and so before I go to the lectures, again, just wanted to impose on you that if you do consider when they're having a lecture right now for the summer student, can I go back to your office? Sorry? No, there's no change in schedule. Sorry about that. So for the a career in astronomy, you need to have a very thorough and clear understanding of how radiation behaves, what are the methods of radiation that we can perceive, and how do we actually observe these radiation mechanisms. So in this set of lectures, I'll mostly be talking about the radiation mechanisms. And as you have further lectures in this summer school, you will learn more about how we can observe this radiation through different telescopes, the methods of observations, etc. And I'm sure there will be some demonstrations as well in some of the afternoons on optical telescopes, on radio astronomy, or catching radio waves and getting information out of them, etc., etc. So before we go into the radiation mechanisms, I just wanted to impress this particular slide on you, that the visible sky that we see is not really transparent to all wavelengths of light. Now, as you know, the electromagnetic spectrum has a wide range of wavelengths or frequencies, whichever we call it. And the way we view the night sky is mostly through the visible light with our eyes. But all of these astrophysical objects, they emit radiation at different wavebands. And for example, then that is why it's very important to understand which of these ranges of radiation are actually visible to us. And if they're not, then we'll have to devise different methods to observe this radiation. For example, starting from the larger wavelengths. So these regions are actually the ultra high frequency ranges, and they are opaque to the atmosphere. So the main problem that we have is this thick atmosphere that is covering the Earth. It absorbs certain wavelengths of radiation and makes the sky opaque to those radiation wavelengths. So this, the very long wavelengths are absorbed, but we have a transparent window in this regime. And this is where a very important class of telescopes called the radio telescopes operate. They are the same kind of principles that you have for your mobile phones or major amount of communications that happen on Earth. But it's also the same frequencies and wavelengths are also used by the astrophysical objects to communicate with you by sending their electromagnetic radiation. So there is a big region where it is transparent, and we have ground-based telescopes in the form of like this, where you have dishes of antennas, metallic antennas, which focus the radiation coming towards it onto a central receiver here. And then it is using several electronic equipments that is then understood of, we can infer information about the radiation that is coming here. So this is a transparent window, but then it is this region that is slightly opaque. You can see there are some small spikes of bands where it is still transparent, but it is mostly opaque. And this is the infrared region, or the IR. So this is a very crucial band where we get a lot of information about the extragalactic or even the galactic environments, especially say dust grains or even synchrotron emission from you must have all seen this nice ring of the black hole that is at emission frequencies of 230 gigahertz, and that is exactly somewhere around here. So these regions are all opaque, but there are two ways of how you can observe infrared radiation coming from outside the Earth. One is through space telescopes. So you send a telescope to space. It is outside the atmosphere, so the atmosphere is not absorbing it, and you're obtaining the information. Or you go to some place where you have a high altitude. Now, as you know, the altitude increases, the depth or the thickness of the atmosphere decreases drastically. So there are several such telescope facilities now in the planet where we have set up telescopes on the top of mountains. One such facility is called the ALMA, and you can read about it more on the internet if you have access to the web. And you'll find that it is one of the highest telescopes. And personally, when I've talked to people, they have told me that they cannot work at the ALMA, or the instrumentation team cannot work at the ALMA for more than a few hours because of the lack of oxygen. They have to come down to the base station, resupply, and then go back, work for a few hours, and come back again. But the advantage is all the water vapor and everything that absorbs all this infrared radiation that is below the level of the telescope, and you can get a clearer image of this of the universe. So these are the infrared bands, and then it's the optical. And optical bands are, of course, visible and transparent to the atmosphere, and that is why we can see the cosmos. And then we go to the higher frequency or shorter wavelength. So these regions are called the high energy astronomy and astrophysics. There will be some lectures towards the end of the summer school, some specialized lectures, say on gamma ray astronomy or even X-ray astronomy regarding stellar mass, black holes, etc. But it is this region, and again, as you can see, this region is again opaque. So sitting on Earth, you cannot build a UV telescope. It is simply not possible because you will not see anything. All the UV radiation that comes is more or less absorbed. Of course, not all of it, because the sun gives a strong amount of UV radiation, but the faint UV radiation coming from extraterrestrial sources, that is absorbed. And of course, then you have X-rays and gamma rays. And for all of this, for all telescopes in this region, we have to go to space. Even telescopes at high altitudes are not enough. So we have to go to space and set up space telescopes to infer information about them. So this is the scenario of astronomy now, and this gives you a brief idea of what kind of wavelengths do we focus in. And depending on the wavelength, we are either a ground-based astronomy or a space-based astronomy. And that sort of divides our class of astronomy from the instrumentation perspective as well. And things have different sorts of challenges and complications in both scenarios. Okay, so but no matter what you do, the basic thing that you have to understand is the fact that what you're observing is radiation coming from extraterrestrial sources towards you. And we, in this set of lectures, will understand the basics of this radiation and how we can describe this radiation in some mathematical way to understand the evolution of the luminosity and the intensity, and then measure the fluxes and make sense of what this flux that is measured by these telescopes, what do they mean? So as we proceed, you will learn more about this. But before that, I wanted to highlight to you that broadly, the entire amount of radiation that we observe can be separated into these classes. One is the continuum emission. Continuum emission is emission over a broad wavelength range. For example, and I will talk about this later, this process is later, black body emission, Bremsstrahlung emission, or a mix of different kinds of emission, where there's a broad wavelength range of coverage. And this process is radiation really comes from charged particles. But if you have a distribution of charged particles with their own, with a continuous variation in energy, the emission that you will have will also follow a continuous pattern instead of discrete quantum mechanical structures. So this is called a continuum emission profile. And then you have line emission. Line emission meaning that you have emission over a very narrow wavelength range due to quantum mechanical transitions between these discrete energy levels. And I will again come back to this figure later on, but what this shows is you have two energy states, 1 and 2, and I'm sure all of you have learned about this in your quantum mechanical lectures. And you can have one atom excited to the higher state, and as it stays there for time, there is a de-excitation rate, and this electron de-excites and comes back to the lower states, and as it comes back, it emits a photon of energy. And this photon of energy then travels towards you, but has a very specific frequency. Of course, it is not a unique frequency because there are widths involved, and the width of the wavelength depends on various factors. One is quantum mechanical itself because of the uncertainty principle, which is related to the transition probability here. And there are other physical factors, which I will discuss later on as I talk about these transitions. But then what you usually observe in an actual spectrum is a mix of both line emission as well as continuum emission. So what I'm presenting here is a very standard spectrum of an AGN in the UV region, let's say. Quasar is AGN, and you'll learn more about it, what are quasars and what are AGN. AGN is a short form for active galactic nuclei. So these are supermassive black holes at the centers of galaxies, and they are extremely large in masses. So the size of a supermassive black hole in the large-scale galaxies can range from 1 million solar mass, like we have in our own Milky Way, to 1 billion solar mass or more. And all the supermassive black holes can accrete matter from surrounding gas all around it. And as the gas starts falling in, it gets hotter because it's getting compressed in a smaller region. And as it gets hotter, it starts emitting radiation. So this is the radiation that you see. And this radiation is mainly powered by the gravitational potential of the supermassive black hole, because the potential energy is converted to kinetic energy, and that part of that kinetic energy is converted to heat. And this heat is then sort of perceived. This is a very glossed over way of saying it. It's not exactly the heat energy that you perceive it, because this is converted to other forms of energy due to several different interaction processes that I will talk about later. But this is how you can see the centers or the emission coming from the center of the galaxy. And what you can see here is a typical spectrum. Now, if you look at the shape of the spectrum, if you forget the red lines that I've drawn here, first of all, looks quite jagged. And then there are these spikes at certain locations. But if you can try to plot a mean line over here, you can see that there is a line here. And then there is another continuous line here. So the spectrum on its own has a shape. And this is the shape. So it's a flat in this wavelength, and then there is a falling spectrum here. So this basic shape of the spectrum is what we call the continuum emission processes. So as the matter is falling inside the accretion disk, it becomes hot and it starts emitting radiation. And all this radiation is then sent out into space. And since this is not a unique transition, because the matter is hot, so it have a wide distribution of energy. And that is why over the entire UV band, you have a continuum process. But besides this continuum process, you can see there are excursions here, which are like spikes sticking out. And these are emission lines due to transitions of certain elements. For example, they have marked here, this is from a paper by Zhang et al. In 1997. And the spectrum is obtained using the Hubble Space Telescope and using the AJ-COS instrument. And you can see this is the emission line for carbon-4, this is magnesium-2, iron-2. Lyman alpha is for hydrogenic transitions, and the Lyman alpha series and the beta series and other elements. So all these are spectra. And this is what I'm talking about. So in any actual observations, you'll have a continuum emission, and there are line emissions here. And besides continuum and line, so all of these are extremely vital to gain insights about the astrophysical object. For example, if we know what sort of basic processes are contributing to the continuum emission, we can understand various important parameters about the gas that is falling in. For example, let's say, if the gas that is falling in has some finite temperature, and it is this distribution of temperature that is giving out this continuum emission, then just by fitting this continuum function itself, we can gain some information about the property of the gas that is falling inside the black hole. Besides that, as you can see from the peaks here, the line emission, they have a finite width. And I will talk more about this when I discuss line emission later on in the series. From this width, what you can actually find out is the velocity dispersion of the gas that is emitting this region. And how do you do it? Because as we know, quantum mechanical transitions are extremely fine and narrow. So they have an inherent width that is related to the uncertainty principle and the transition probability here. But that is extremely small, much smaller than the width that you see here. The width you see here is because different atoms are moving at different velocities, and they result in something called the Doppler width. Because one atom is moving towards you at one velocity. So the emission energy that is coming towards you would be slightly different from the basic transition in the rest frame of the atom. Similarly, one atom that is going away from you will again have its energy slightly shifted. So if you have a convolution of these different emitting systems, then you get a width. And by understanding this, we can find out how dynamic this system is. Or the velocity dispersion is another way of saying what is the turbulence in the system. How much of a breadth in the velocity structure do we have? If all of them were moving with the same velocity or speed, then we would have a much narrow and thin line, but that is not the case. As you can see, they have broad widths. So these are the things that we do by fitting these lines. Then we can find out the width of the lines, and we can then infer some specific quantities about the source. So just by looking at these two spectrum, as you can see, we are already trying to infer various important physical parameters of the source itself. And this is how we can infer things about astronomical objects. Another important thing is absorption. Now, I have talked about radiation. That is when you have something that is excited in our different higher level states that comes down and emits a photon towards you, and that is called emission. But suppose that the emitting source is behind a screen of gas. Now, once it emits, it has to pass through the screen of gas, and then the gas itself can have excited regions like this, or can have neutral atoms here, which are in the lower state. And once those photons interact with these neutral atoms, they can excite them to make an upward transition. So those photons will get absorbed by the gas. So absorption, I'll come to in more detail later on, but this is another very important method by which we can understand things about the cosmos. So gas in front of the emitting source absorbs the radiation, and you can see these are two spectra that I've taken. This is something called the Lyman alpha forest, where you can see there is a basic quasar that was at very high redshift, meaning very far away from us at very early times, and it had emitted some light with some spectrum like this. And that spectrum is coming towards us, passing through a lot of intergalactic gas. And as it is passing through gas at different locations or different redshifts, you will learn more about redshifts and their implications later on in a cosmology course. But all of these will have their own frequency at which they will start absorbing this radiation. So you see, each of these absorption lines correspond to some parcel of gas that has been in the path of this line of sight towards you. So as a radiation was, radiation meaning a bulk of photon was emitted towards you, let's say. And at each location, a fraction of them are getting absorbed. But they're not at the same frequency because, as you move, as you go away from the source, the wavelength at which absorption will take place depends on the distance and the velocity offset, which is called the redshift dependence of the wavelength. So all of these give you some information about all the gas that this radiation has encountered before it has come towards you. And you can see similarly, you can also find out, so this is just Lyman alpha absorption, but you can also have absorption of specific elements. For example, carbon 4 here, silicon 4 here. But more specifically, for example, you're observing, say, the central region of the black hole once again. So the emission from the accretion disk near the black hole is emitting some radiation towards you. But that radiation passes through a cold gas that is absorbing the radiation. And this is one such example. This is called a magnesium-2 or Mg2 absorption. You can see a very clear dip in the profile. So this is the continuum that has been fit, and there's a clear dip in the profile. So there are two things immediately that we can understand from this absorption profile. Sorry about this. Firstly, you can see that it is not at zero. It is slightly offset so there's a bulk offset of the absorption. What this shows is the gas or the blob of gas that is absorbing this radiation coming from the black hole is not stationary. If it was stationary, then it would have been zero. But it itself is moving, and so this is a blue shift. It's a positive velocity, so it is moving towards us. which means that there is an outflow from this, or there is a wind from the central AGN. This is how we start inferring things in actual astronomy. So there's a wind from the central region that is pushing gas out, and the gas is moving at almost, let's say, 150 or so kilometers per second. And then this gas is cold and neutral. That's why the radiation coming from the AGN is getting absorbed here. But we can also gain some insights about this small blob or cloud of gas because it has a width. It is not a very fine transition here, but it has a finite width. And from this width of the gas, we can find out what is the velocity dispersion inside this gas, or in more or less technical term, what is the range of velocities inside the gas with which the material inside the gas itself is moving about. So the gas blob cloud is moving as a bulk speed, but inside the cloud itself, different particles are moving in random orientations. And that is the width with which will be reflected in the absorption profile. So these are the various ways we start inferring about the physical system. So understanding how the radiation is propagated is a basic fundamental nature, a fundamental principle by which we can probe this physical systems. And so this was just a preliminary introduction to you to impress upon you the various kinds of absorption that is required. So now I will go into a bit more mathematical detail, setting up the basics of the formalism of radiative transfer. So when we actually try to model the radiation, what we do is we assume some sort of emission from a source far off, and that emission has to pass through a specific length of space and then reach the observer with the telescope. So we need to understand how this photons, or the intensity of the radiation that is emitted at source, how it is changing as it is passing through a spatial location and reaching the observer. So this is the overall motivation of giving you the more formal mathematical treatment of understanding radiative transfer. So first of all, some basic definitions. I will continue the lectures for 5 more minutes and then take some questions if you have any. So some basic definitions. First of all, what we will talk about this. So this is just to set up the language with which we'll approach the subject. Okay. So firstly, it is something we define something called the specific intensity. So specific intensity is the energy. So suppose you can all see this figure here, I'm sure. So you can see that you have an area that is, so let's say an imaginary area over here, delta A or dA, through which a radiation is passing. Now the specific intensity, or I nu as it is used in the standard literature, is the amount of energy, delta E, passing through per unit area, so dA, per unit time, so dt, per unit solid angle, and per unit frequency. Solid angle, why? Because this area can have a normal in this direction, but through this small patch of area, you can have rays that are going in all sorts of directions, because rays can have from a different particular source. For example, let's say a sphere. It is isotropically radiating. So all the rays will be perpendicular to the radius, will be along the radial vectors, or perpendicular to the surface of the sphere. So if you just take a small area, you'll have rays crossing it at different directions. So that is why what we define is the intensity per unit solid angle. So that is the energy per unit solid angle is what we call the intensity. So this is just a definition of what intensity is. Now, as we proceed onwards, you will understand how we can connect this definition of intensity to other physical processes and try to understand the fundamentals of the system itself. And then what we define is something called a flux. So flux is the total amount of energy passing through an area dA per unit time, per unit frequency, integrated over solid angle. So flux is nothing but integration of the solid angle plus a cos theta term, because what we want is not just solid angle towards a particular direction, but over the entire area. So I nu cos theta d omega. Okay, so it is the total amount of energy. So since it has a solid angle dependence per unit area, so that's why you have to multiply by cos theta, because intensity is always defined with respect to the area normal to the ray. Okay, so dA is this dA in the definition of intensity. It is the area normal to the direction. So suppose if you have a generic area over here, and the intensity over this region would be dA cos theta. Okay, so that is why you have to multiply by cos theta here and get the flux. Fine, so these are all some basic definitions. Now, what is the relation to the energy density? Now, the total energy that is passing through the surface area is I nu, which is the intensity, multiplied by the solid angle d omega, times the time dA dt and cos theta, because again the cos theta is coming here because you have to make sure that the I nu is defined with the area that is perpendicular to the direction. So this is the total energy that is passing through the surface. So energy per unit, so and also, of course, if you want to kind of consider the energy density or the energy per unit volume, then if you take this area in time, in per unit time, amount of photons that are passing through it will travel a length of c times delta t. So if you have a small time delta t, the total length of the photons or a volume element in time delta t that the photons will cross and create this volume element is c times delta t. So the unit volume can be defined as c delta t dA cos theta. So the total energy density along this pencil beam then would be this total amount of energy that is passing through this area per unit time in the time dt and divided by this volume. So now we have a unique way of understanding how the energy density is related to the intensity. So as you can see, the energy density U omega, so this is per unit solid angle, and that's what the definition is related to the I nu by C. So U omega, so if you find out the intensity of the system in some way, you can relate it to the energy density or what is the energy per unit volume. And U omega is I nu by C. And then there is another definition that is often used in astrophysical texts, which is called the J nu or the mean specific intensity. This is the I nu or the specific intensity integrated over all solid angles divided by C. Okay, so these are some of the basic definitions that we will use in our lectures. Now, this is an interesting point, which is called the inverse square law. So we all know that radiation that is emitted by a system that is conserved when integrated over the area, so that the strength of the radiation falls off as 1 by r squared. Now, this you can easily demonstrate using this simple system over here. So suppose you have an uniform sphere of radius r with intensity I nu on the surface. So, but since it's a uniform sphere, in the intensity of all the rays coming out from the surface of the sphere is all same, which is I0. Thus, all the rays that intersect the sphere have the same specific intensity. So, going back again to the definition of flux. So, the total flux is you take the intensity, multiply by cos theta, and integrate over the entire solid angle space. So, this gives you the total flux. Now, for an observer at point P, what we want to find out is what is the total flux that the observer at point P experiences. Now, the observer at point P will not really see the whole of the sphere. They will see only a fraction of the sphere, which is given by this extension of this angle theta c, which is a tangent to the sphere at these 2 points. So while performing this integral, we will only consider the angle going from 0 to theta c. And these are just mathematical jargon. I'll upload these notes later on in the PPWorks website where you can follow the mathematics. What you will find out is, since the intensity is uniform for the sphere and the same at all points, you can take the intensity outside of the solid angle distribution. This is the isotropic distribution of intensity. And just performing this integral over the trigonometrical quantities will leave you with the fact that it's sine squared theta c, this theta c quantity, which you can relate to the radius and the distance from the center of the sphere. And you end up with something like this, which is the flux observed at point P is inversely proportional to square of the distance from the center of the sphere. Now, what is important to note here is, so this is the standard inverse square law that we find, and we can readily find it from the basic definition of what the flux is and what the intensity is, and the fact that we are considering a uniform sphere with same intensity everywhere, which means it's isotropic intensity. If it's not isotropic, then the intensity will not be same at all points on the sphere. Now, there's an interesting point here. Suppose you take r, the small r, which is the distance from the center of the sphere to the point, equal to the radius of the sphere itself. That is, you're trying to find the flux at the point of on the sphere, at any particular point on the sphere. If you do that, you will find that F nu at the surface of the sphere is pi times I naught. Now, this is again a fundamental relation that we have in the understanding of radiation transfer. That is, the flux is related to the specific or the uniform specific intensity as pi times I0. And we will come back to it again when we discuss black body radiation, because this relation will be used to define certain quantities. So I think we have 5 minutes before 11. So we had a slow start today because we had to spend some time discussing the prelims and basics. But I will pick up things from next lecture onwards, and I will see if you have questions right now. So let me unshare the screen and go to the participants tab. Okay, so Junik has a question, so I'll unmute you first. Junik, please go ahead.
Thank you, sir. First of all, it was a fantastic lecture. And sir, the question that I have is from the first part of your lecture, when you said that the optical band is transparent as well as the radio band at some certain ranges. So what makes the optical band so transparent at those ranges and the radio bands transparent? I mean, both of them, everything is, the entire spectrum is EM spectrum. So what makes part of this transparent and the other ones not?
Please specify what you have to understand is why it is opaque at other wavelengths. I think that is your question. And it is because of the atmosphere. An atmosphere has certain composition. And it is built with water vapor and different molecules. And all of these have resonant frequencies. And these have a distribution of resonant frequencies which can absorb certain frequencies. And since it is not just a simple distribution of molecules, have many different composition, all of these sort of absorb all this radiation. And then you can, since you're asking this, you can do this very simple experiment of taking the, say, a typical density and find out the mean optical depth inside the atmosphere. You will find that all of these would get absorbed. So it is just these certain ranges where the atmosphere doesn't have these absorbing elements. For example, I can tell you, especially for the infrared bands, a big problem for this, especially this band, if you can see my pointer, is water vapor. Yes. The water vapor absorbs these regions, which is several hundred gigahertz, I think. And this is something related to the millimeter wave astronomy. And we use this actually to study water vapor and molecules in outer space. We do observe CO and H2O and other host of other molecules. These are just some examples I'm giving you in outer space. But all of these will actually, since we're observing them, they will get absorbed by the distribution in the molecule in the atmosphere itself. So that is why I was saying this. There is this very fantastic telescope called ALMA, which is located at very high altitudes. And since it's a high altitude, the distribution of the atmosphere is not really linear. It goes exponentially declines, and then beyond the troposphere, it has a certain declination. So another way people actually observe this infrared region is they fly an aeroplane. It's called SOFIA, S-O-F-I-A. You can look up the internet. Very nice, fantastic pictures. And there's a very nice picture of the SOFIA plane itself. So they have mounted a telescope at the back end of this aircraft. And as it goes beyond the troposphere in the stratosphere region, as it is flying, it points its telescope towards its astrophysical sources. Because once you clear the troposphere, you are in the low density region, where the optical depth, and again, I will talk about optical depth later on in this lecture series, but many of you would be aware of what that is. It becomes transparent, and the optical depth is not one anymore. So that's why you have certain windows that are there. But the main reason of why this absorption is taking place is because of certain elements and molecules inside the atmosphere that absorbs at certain frequencies, and overall, this thickness of the atmosphere as well as the dust that provides a continuous absorption of all the radiation that comes towards you. Okay.
Okay. Thank you. Thank you.
Thank you, Jenny. So, Astha, next, asking you to unmute yourself.
Yes, sir. Am I audible?
Yes.
Yes, sir. As the bodies in space emit black body radiation, so when observing the emission and absorption spectra, how do we decide the wavelength range?
Astha, can you repeat the first part of the question? You got cut off.
I was saying that as all the bodies in the space emit black body radiation, and there can be different gases, different types of gases that absorb some of the part of the radiation. So how do we decide that which wavelength range we have to observe for observing emission and absorption spectrum?
Right. So this is a very good question. So let me go to the absorption part. Yeah. So firstly, not all of the radiation outside is black body radiation. Okay, so we have different various kinds of sources of emission. Black body radiation is one of the continuum sources of emission. So are the other mechanisms such as bremsstrahlung and others, which I'll talk about later, maybe in my third lecture. So it's not so if the entire region is getting absorbed, then you have a total decline in the emission in the observed radiation, and this does happen. For example, if you have very dense distribution of clouds, all of that radiation from depending on the impact parameter or the absorption coefficient of the cloud, which is also of course also dependent on the frequency. So while modeling the spectrum, especially for let's say for the X-ray spectrum, which have a strong dependence on absorption on the column depth of gas, the entire radiation comes down. So while modeling the spectrum, we have to model a wide range of absorption quantity or absorption function that reduces the emission over a wide range, not just simple, a spectrum like this. However, you can also have absorptions from certain molecules. So even if you have a continuum emission from a black body that is coming in, let's say, the absorption will only occur at that particular wavelength. So Astha, unmuting yourself again, just to see whether you can, if I've responded to the question. So as the radiation is coming in, so even if it's a black body radiation or continuum radiation, the absorption process itself occurs at a particular frequency or wavelength. Okay, and so it's not just the fact that the entire region is getting absorbed, and this happens when you have absorption from a particular molecule or a particular element. And that is why you see these lines here. So absorption can happen in two ways. You have a broad absorption due to the column depth of the gas, or you can have absorption at specific wavelengths. Okay, so I hope that was clear. Astha, I'm unmuting yourself again.
Yes, sir. Thank you so much.
Thank you. Anushka, next, please unmute yourself.
Yes, hello, sir.
Yes.
In slide numbers 7 and 6, while considering the mathematical expressions for
Yes.
flux and other things, what we assume was from the emitting body and to the observer or to the absorbing body, the transfer or the travel of the rays, energy rays that takes place are linear. But we know that in actual cosmological environments, the more the massive the object gets, there is deviations in the fabric of time and space, and so the rays get deviated in themselves. So in such places, when we apply these concepts, do we continue with the assumption that the rays are traveling linearly, or do we modify these mathematical expressions accordingly, or just for the sake of keeping them simple, we keep assuming that they are linear?
So what you are talking about, let me rephrase your question, Anushka, that the basic point that you have is if you have an array of intensity that is going, traversing space, due to a variation in the space-time curvature itself, there can be changes in the intensity pattern. Now, I will, in the next lecture, I will also demonstrate that for a constant space-time, so I am not considering any curvature in this lecture, and I'm not sure if the GR lectures will cover it as well. But in this lecture, we'll always consider normal space-time, which is all flat. So in that, I will demonstrate tomorrow that intensity remains constant along a particular ray. Okay, so in this approximation of a flat space-time, intensity is constant, and I'll demonstrate that mathematically tomorrow as well. However, I will again show the derivation of this equation. This is how the time dependence and space dependent evolution of the intensity distribution actually takes place in normal space-time. Again, this is flat space-time. You can see this is it's a partial differential equation with an emission and an absorption term. There are spatial derivatives of the equation. So when we model this in a GR kind of environment, for example, say we're trying to model the ray that is emitted from a black hole, from some region near the black hole, and that is traversing the space coming towards us, we modify this fundamental equation to take into account the evolution of the metric itself. So in that cases, what we can do is over small patches of space, we can assume that the space-time is constant. So this is called the local approximation. So over that region, this is valid. And then we apply a metric to transport this intensity over the larger region. So you're very right. But in this particular lecture, we will not consider any distortion to the intensity due to space-time. Thank you.
Thank you, sir.
Okay, Anik, next, please unmute yourself.
Hello, good morning, sir.
Good morning, Anik.
Sir, I have a simple questions that you have said that suppose there is a source which is emitting specific radiation of certain wavelength, and now in between the paths we have a cloud which is also emitting the same sort of gas. How we will differentiate the spectrum?
Anik, sorry, can you state the question again? Because what you're saying is that you have two different clouds emitting the same region of the wavelength.
Sorry, sir. I'm saying that suppose we have an emitting source, okay, for which we are measuring certain wavelength, say hydrogen. Okay.
Yes.
Now, when the radiation coming from that source, and in between somewhere you have another same source, a hydrogen cloud, suppose. And now we are looking at the spectrum. How we will differentiate?
Those are very complex situations, Anik, and you are very right. Those situations do occur. What we try to do is we have then suppose we are talking about a single emission line profile. We can have contribution to that emission line from different regions. Now, since suppose if you're talking about intervening gas, if it is just hydrogen and if the gas is very far away from that emitting source, there will be a shift in the frequency because of the Doppler shift.
Yes.
So that will not really contribute to the emission of for the first source, let's say, although it can lead to absorption. But however, if there are multiple emitting sources very close to each other, they can have actually an overlap. And in those cases, what we end up with is not a simple sharp rise and fall phase of the spectrum, but a complex shape of the spectrum. And we try to fit that spectrum empirically with several different components, and then try to decompose the spectrum into different components to try to understand whether we can separate out these two emission regions. And then we do that, actually. If we have the good statistics, and if our fitting method gives unique solutions, then we can do that. But sometimes we cannot do that. And we are constrained by the fact that we are not resolving the region. So then the option is to go for higher spatial resolution to separate out these two components and then try to see them again. So these are actual challenges we face in actual observations.
Okay, sir. Thank you, sir.
Utkarsh, next, please. I'll ask you to unmute yourself.
Good morning. Sir, I have a doubt on the lecture 4 slide. Slide 4.
Slide 4, yeah, okay, yes.
So in this diagram, what is the significance of the red lines which are there?
So these are just, I have drawn by hand. Okay, so there is no significance here, but as I was trying to say was, you can see that there is a basic shape of the spectrum itself. So the spectrum is defined by these jagged lines here, and these small excursions are due to noise, because you have photons that are coming, there's finite Poissonian distribution, and that is just noise. But overall, if you integrate or average out the spectrum, you can see that they follow almost a straight line here. And then in this part, you can see there are emission lines, but then the basic template also follows a sort of a power law distribution here. Okay, so this was just to guide your eye that there is a basic shape of the spectrum. And if you forget the emission line, so suppose I remove this emission line, you will still end up with something like a flat top and a power law. And this is very typical, and this is what I was saying, that this is due to the continuum emission processes. And these spikes are due to emission lines. Okay, so this is the continuum emission. Okay, so this was that. And Poonam, next, please unmute yourself.
Yes, sir. It was a fantastic lecture today. So we saw a inverse square law. What is the probability, or we can say, when there will be a condition to get the r is equal to small r is equal to r?
Oh, this is just a theoretical construct, Poonam. So it is not a probability of an actual physical thing happening, that you go to the surface of the sun and then measure something. But this is just the way we are trying to develop the mathematical framework. And what we can see that the flux, as we have defined it, is related to the intensity for an isotropic distribution of intensity in this way. So in later works, as I try to connect this I knew to some basic physical processes, for example, say electrons are moving about and they emit charged radiation, and that radiation is coming towards you. And all of this, then I can integrate to find that the intensity, or the mathematical form of the intensity I knew. Then it will be much easier for me to understand what the flux would be, or what is the relation between the flux and the I knew. Because as you know, I knew, as I have defined it, is the intensity per unit area normal to that ray, per unit solid angle, per unit time, per unit frequency. But the flux is solid angle averaged, or integrated over the solid angle. So this is just a relation between I knew and F. It has nothing to do with the physical situation. Okay, Nikhil, I'm unmuting you. Please ask your question.
Hello.
Yes.
Hello.
Yes, Nikhil, please go on.
So, sir, it's not really a conceptual question, but rather a mathematical.
Yes.
So, can you hear me, sir?
Your voice is cutting off, Nikhil. Yes.
Hello.
Please go on. Please go on, Nikhil.
So my question isn't really a conceptual one, but rather a mathematical one. Can you just go to the slide where you explained specific intensity and flux?
Yes, this one, yeah.
So we can see that delta E is expressed in ergs, and dA, dt, d omega, and d nu. All these have these values, the units. So some are CGI and some are SI. So how do we really? So is that really flexible, or we can just?
Which one is SI here?
Sir,
seconds, or because see, ergs is in CGS, centimeters CGS. Steradian, I don't think there is any difference between CGS and SI. And hertz and seconds are just seconds, so it's the same.
Sir, is this a standard of using, or do we use CGS? Or are we just using SI?
No, the thing is, in astrophysics and astronomy, you will mostly find CGS. So the way that I have defined the units here, this is the way things are defined. So even if you say that it's a mixing here, I don't see any mixing of SI and CGS, but this is the way it is defined. And this is the definition that is carried forward. But I'll just also warn you that in astrophysics, we mostly deal with CGS units. And this sort of comes from more traditional perspective because astrophysics is an old subject, developing from the 60s and 90s, or even earlier, much earlier than this. And so there people were more tuned or accustomed to using CGS units. Whereas the more modern developed sciences, they use more SI units because they have evolved much rapidly in the later periods. So in astrophysics, we mostly use CGS units or specialized units that are relevant for astrophysics itself. For example, we define length scales in terms of parsecs or kiloparsecs. We don't really use centimeters and meters because there's a very large number, but we use parsecs and kiloparsec that also becomes quite large, but it is manageable. So this is the way the units are defined. Okay. Okay, so then Arjun, please ask a question.
Hello, sir. Can you hear me?
Yes, Arjun.
Sir, thank you for the lecture. Sir, my question is again from the slide 4.
Slide 4, okay.
Sir, here we can see that the continuum emission goes down as we approach to the higher wavelength. So, sir, what we can infer from this variation, or is it a particular property of AGN or something else?
This is a particular property of the emission mechanism that is taking place here. Okay. So the basic, as I will show you some of the basic emission mechanisms, you will find that they don't have always just a simple power law dependence, but can have a rising phase in the spectrum and a falling phase in the spectrum. And that depends on the nature of the emission mechanism itself. So right now, let us not infer too much about what is the emission mechanism of this continuum process. After I have discussed the various emission mechanisms, maybe I'll come back to it to talk about the basic continuum emission processes inside the AGN. Okay, maybe the last question, because I'm running out of time. Shreya?
Good morning, sir.
Good morning.
My question is, when we talk about black holes, there is a different world around there in the black hole, inside the black hole, and the things entering the black hole when the gas enter the black hole. So it can change the its property. So how through the radiation that come out encountering that gas, we can found about the property of that gas.
So firstly, the emission, Shreya, that we are talking about here from the black hole is not exactly coming from inside the black hole. Once you fall inside the black hole, nothing can come out. What we're talking about is the gas before it falls inside the black hole. Because as I said, as it is falling inside the black hole, because of the potential energy of the black hole, it is gaining a lot of kinetic energy as it's converting the potential to kinetic energy. And that kinetic energy is also getting transferred into internal energy, or the heat energy, and other emission processes. So it is the gas that is falling inside, that is about to fall inside the black hole, but not inside the black hole yet. And that gas becomes very hot. And that hot gas emits radiation, which is further interacts with the gas all around it. So, for example, the black hole inside, matter accreting a falling into a black hole is often found in accretion disks, in a disk-like structure because of the angular momentum. Now, emission from this disk goes above and below the disk, but all around it, there is a very high temperature hot gas, like a halo, where this emission will interact. So this will produce emission by something called Compton interaction. I'll talk about it later on in the 4th lecture. So this Compton interaction, so this emission from the falling gas is getting reprocessed by the gas all around it. Some of these photons produced due to this Compton interaction will fall back onto the disk itself and get reflected. As it is getting reflected, the emission pattern is getting changed. So all of this together gives you final spectrum or the final emission that is coming towards you. So none of the emission towards you is actually coming from the black hole, but it's the vicinity of the black hole. But even from this, we can get significant information both about the gas falling into the black hole as well as the properties of the black hole. Because if the gas is coming very close to the inner edge of the black hole, we can understand what is the rotation speed of the gas. And if we can do that, we can then constrain the mass and other properties of the black hole itself. So these are various things that we use to probe systems like black holes, but nothing comes from inside the black hole. Thank you, Shreya.
Thank you.
Maybe the last question, Ishika Chand.
Yes, sir. So in fifth slide.
Yes.
So what actually is this velocity in the magnesium absorption spectrum?
So this is this should be the wavelength of spectrum, but I will try to talk about this. You might have studied, or you will study something about Doppler shifts, where if your emitting region or emitting source is moving away from you or moving towards you, there is a shift in this in the rest frequency, and that is related to the velocity. So when we actually plot a spectrum in astronomy, we don't really plot it in terms of the wavelength. If we are focusing on a particular line, let's say, if we are plotting the entire spectrum, then we of course plot the wavelength. And at each of these wavelengths, we try to fit the spectrum. But if you're just focusing on a particular line, we directly convert the wavelength into the velocity with respect to its rest frame velocity. So at its rest frame velocity, if the emitting source is at zero velocity, so that would be its natural wavelength of absorption, and that is a zero velocity. It is if it slightly moves away from it, so there is a Doppler relation. It is not there in my slides today, so I can't show it to you, but I will mention it to you next time. So that the delta lambda, the change in the wavelength, is related to the delta velocity by c. So this is something that we use to just transform the x-axis from wavelength to velocity. Okay, thank you all, Ashika and others, for the questions. Unfortunately, we'll have to take a break now because the next lecture is starting in 10 minutes. So I will close this lecture. If you have any questions, note them down. We will try to see if we can take these questions from you and address them later on. So thank you once again, and see you for tomorrow's lecture, and you will have the next lecture in 10 minutes from now. Thank you.